2-6 notes on transforming linear functions, and we are going to do other functions that we transform. So this is the beginning of learning transformations, and you will do more of this in the next couple years of your math courses. All right, so we have a vertical and horizontal translation. Now remember from geometry, a translation is just shifting up, down, left, or right. That's a translation, just moving something. So translating a linear function vertically or horizontally changes the intercepts of the function, but it does not change the slope. So we're not twisting or bending or making it steeper. We're just picking up our line and shifting it up, down, left, or right. So if you have a horizontal translation, horizontal is going to move it left or right. So here's how I remember it. If you think about your x-axis, isn't that the one that moves left and right? So to remember it, if it's paired with x, it moves the x value, which moves it right or left. So see how the h is paired with the x value. Okay, what did f of x stand for? F of x is the same as y equals, but we say the function of x. Okay, so we have a function, but instead of just having x, we're going to have x and we're going to take away the value h. Now, I know it says minus, but it's the opposite. So if it says x minus h, we're moving the function right h units. If it says x plus h, we're moving the function left h units. You're going to talk about this later, but the idea is the standard is x minus h. So if I have x plus h, that must have come from x minus a negative h. And that's the idea. So the function is always x minus, and then we put the value here. So this, the h is positive, and in this one, it must have been x minus a negative, and that turns to a positive h there. So that's why some of you will just remember it moves the opposite direction. Now, the vertical translation moves the y value, and y is up or down. So here it is, f of x is the same as saying y equals, right? If I add something to the y value, it is going to move up. If I take something away from the y value, it is going to move down. So the h is what we pair with x. If it's paired with x, it moves x, left or right. And some of you just remember it does the opposite. It's doing the opposite because the function is always x minus. And then we have the h value. If it's outside, we have the y value and we say we're going to add something, it will move up or move down. So k is the up or the down value. Now, if you think about this, it's going to move sometimes up, down, and left or right, or sometimes one way or the other. So look at this original graph. The original graph is f of x equals 3x plus 1. So let's graph that. Let's just use our slope and our y-intercept. So slope is 3 over 1. Y-intercept is 1. Plot that on the y-axis. Rise 3, run 1. I think I just did not write 1, 2, 3. Okay, ignore that point up there. And then sketch in your graph. All right, now, if you look at this, the original function was 3x plus 1. What has changed? Now you have your x minus 2 and you have a plus 1. So this moves 2 units to the right. That's the horizontal translation. And then we have this little plus 1 on the end, but we would have to distribute this and then clean it up, and then we can see what really happens. So if you think about this, you've got this here, and we would do 3 times x minus 6 and then plus 1. And what would you end up with? No, not that. 3x what? Minus 5. Okay, so we're going to take this line, and it is going to start at negative 5 on the y-intercept, and we're going to rise 1, 2, 3, and run 1. 1, 2, 3, and run 1. And I'm just doing it a couple times to have an accurate graph. Okay, so graph that, and let's see how it has changed. So you guys told me that the graph was going to move 2 units to the right. Did it? Yeah. Look at your original, 1, 2. Look at your original, it moved 2 units to the right. Okay, so from our original line red to this one, it did move 2 units right. So we graphed our y-intercept, but remember, when we graphed this, we had to distribute and clean it up. So it looks like the y-intercept changed, and it did, but the big change was right here. The +1 stayed the same, didn't it? The +1 didn't change. Okay, now look at the next one. Why is this a vertical translation? Because we added on that 4. So this is like that k value. Okay, so clean this up. H of x, nothing to distribute, is 3x plus what? Plus 5. So plot your point on the y-intercept at 5, and you're going to rise 1, 2, 3 and run 1, or go down 1, 2, 3 and go left. All right, draw your line. Now all my lines are parallel because the slope stayed the same, right? So that would give me all parallel lines. And now that I have this, now someone might say, well, this moved 2 to the left. Well, did it really? Can my lines line up that nicely? But if we take it, it moved up how many? From the red, 1, 2, 3, 4. So it did go 4 units up. All right, so in this one, k was 4. That was the change. So if I gave you 3x plus 5, you guys would have to realize, oh, it's 4 units different than it started. And in this one, the h value was 2. Now, I don't see that when I see the 3x minus 5. I have to look at the original. All right, go to the next one. It's the same original graph, so graph that. Same original graph. And then we need to determine what's going to happen by the rule and then see if our graph agrees. All right, so there's the original. Guess I'll color code that. That is the f of x function. And then the first thing I'm going to do here is do this horizontal translation. How do I know it's horizontal? Because it's paired with the x. So in this case, if you think about it, it would have been 3 minus a negative 2 and then plus 1. See how that is? That means h was negative 2. So that's going to move my graph left 2 units. Now, what does my function actually look like? G of x, and we're going to distribute the 3. And we clean it up when we get g of x equals 3x plus 7. Okay, so I just want to show you that came from minus and negative. That's why the h value is negative 2. If I go to graph this, I'm at 7. I'm going to go up 3 and over 1, so I'm also going to reverse it to negative 3, negative 1, and then sketch in your line. And look at the change. Did we go up, down, left, or right? We went to the left 2. So my red line shifted 2 units. So left 2 units. Okay, then the next one, it's telling us we're going down 4. Why are we going down 4? Well, look at it. That's the k value. It's negative 4. So h of x, clean it up, equals 3x minus 3. Graph that. Up 1, 2, 3. Where am I going? And do we agree? It didn't go left or right. It went down 4 because you took 4 units away. Well, I did not do that right. Okay, I'm good here. My line just went a little too far off. So if you look at this red line, this point here goes down 1, 2, 3, 4 points to here. So each point gets moved down 4 points. It's a little hard to see on that one. All right, so this went down 4 units. So we should be able to look at the function and know what the change is. All right, so that's vertical and horizontal translations. That is shifting the x or the y value. Now, we're talking about vertical and horizontal compressions or stretches. Okay, so if we were looking at something like a parabola, it's really easy to see. If I'm looking at that U-shaped curve and then I graph another one, it's easy to see, hey, that is a horizontal stretch. Or if it's super skinny, we could say that's a vertical stretch. Or we could look at it and say horizontal compression, vertical compression. It's easy to see with these U-shaped curves because they're wider or narrower. With a line, we're looking at the slope, okay? So compressing or stretching linear function changes the slope. How steep is the line? That's what we're talking about there. So a horizontal stretch or compression by a factor of b. Okay, now, see how it says 1 over b times x? So this is changing the slope, and this is a horizontal stretch. A horizontal stretch would make it look steeper or flatter. If I'm stretching something horizontally and I'm pulling it, it's going to look a little flatter. It's not going to be as steep. A horizontal compression would take something and squeeze it, and so what's going to happen? It's going to look steeper. Okay, so think about having a ball of Play-Doh. If we horizontally stretch the Play-Doh, it looks wider and flatter. If we compress the ball of Play-Doh, it's going to make it taller, so steeper. So if you multiply by 1 over b, think about a half. If you have 8 and I say take a half of it, what do you now have? 4. So the y value went from being a high number 8 down to a 4. It's not growing as fast. So on this one, b is going to be something like, let's say, 2. And if I have the number 8 and I say, well, double that, now it's growing faster, so it's 16. Okay, so that horizontal compression is going to make it look like it's steeper. Now, look at the reverse. 1 over bx is a horizontal stretch by b, and bx is a horizontal compression by the factor of 1 over b. So it can get a little confusing with these rules. Okay, so this is a horizontal stretch or compression. Now, if you're talking about vertical, do you notice the value's outside? Okay, so this is directly affecting the x value, where this is take a times the whole function. It's going to give you a vertical stretch of a. So this one follows exactly as it is, and this one is 1 over a times the whole function, and it's going to give you that vertical compression. Now, if I stretch something vertically, it's going to look taller, isn't it? So steeper. And if I vertically smash that Play-Doh, it's going to look wider, so it's going to be less steep. Okay, so let's do the same function. So we're starting out with the same function again, and then we're going to see how it changes. So graph that, sketch in your line. I'm just going to do the other one while I'm at it. So sketch in your lines for the original function. Now this is not the parent function. The parent function would just be y equals x. Now let's change it. Notice that the 1/2 is paired with the x. So here, b is 2. See how it's 1 over 2? It's 1 over the value of b. See how it's 1 over b? So the value is b. So b is 2. And what's going to happen? It's going to be a horizontal stretch by 2. Okay, is it going to be flatter or steeper? If you're stretching it horizontally, you're going to take the line, you're going to pull it sideways. All right, so let's clean this up. Wouldn't this be 3/2 x and then just plus 1? All right, so graph it at 1. So same y-intercept. No, it's not shifting up, down, or left or right, but the slope has changed. Up 3 over 2. Oh, I think I went too far. Yes. All right. So this is your function g of x, and we can see that it's not as steep as the original function was. Okay, we'll deal with that later. All right, so this has a horizontal stretch and factor is like a scale factor, factor of 2. Okay, now look at this one. See how the whole function is 3x plus 1? The whole thing is being multiplied by 2. This is like the factor of 1 over b. So our value would be 1 over 2. Okay, now when you look at this, we're going to distribute it to everything. So it's h of x equals 6x plus 2. All right, so that's changing things a little bit here. The y-intercept is starting at 2, and then you're going to go up 6, 1, 2, 3, 4, 5, 6 over 1. Because we can just look at this. A slope of 6 is definitely steeper than a slope of 3. And a slope of 3 over 2 is the same as 1.5, which is less than a slope of 3. All right, so go ahead, make a couple points if you need to. Sketch in your line. Now, we are just doing these with lines, but all functions, all parent functions can be changed. So they all have these shifts and translations. All right, so this would be a vertical stretch. We can see the vertical stretch, and how do I know what it's by? Because if you think about it, didn't I double the slope by multiplying it by 2? Vertical stretch of 2. Okay, so we made it steeper. So this one is steeper. And this one over here was what? I don't know. Do you want to say less steep, pulled horizontally? Less steep? Flatter slope? All right, last one. Let's talk about these compressions. A compression is basically smashing something, okay? Same idea. This one is changing the x directly. So I already graphed that first one. So we have g of x equals 6x plus 1. So this one's going to, a horizontal compression is going to smash it, which is going to make it steeper. Do you notice that it's very similar, but we have a different y-intercept? Same slope, though. All right, put your point, go up 6, right 1. Draw on your line. A little steeper with a little bit of a move there. Oh, I graphed that red line wrong, guys. I shouldn't have moved. My red line should be down here. This should be my red line. Ignore me. There's my red line. And then my green line's here. Okay. You've got it fixed. All right. My original red line should have been at 1 and go up 3 and over 1, so I have fixed that. My green line comes in, and it is a little bit steeper. Okay, so we have a steeper slope. So if you think about it, if this is considered a horizontal compression, we had to smash that in so it makes it look a little taller. This one, distribute, you have h of x equals 3/2 x. I would really like to keep my slope as a fraction. Now, when I go to point this 1/2, my graph's really messy. You're going to have to go to 1/2. And then when I go to do my slope, I'm always going to be at a half. So I'm going to go up 1, 2, 3, and then over 1, 2. And I'm always going to be at a half. Up 1, 2, 3, and over 1, 2. And again, I apologize for my messiness. Here you go. So this one is a little bit flatter, okay? So again, it would be less steep. Which, if you think about it, 1.5, doesn't that match there? Now, notice the difference here. When you have these horizontal and vertical stretches, it didn't change this y-intercept for this one. But the slope is smaller, so it's going to be less steep. This one, it does affect everything, and the slope is steeper because 6 is a higher slope than 3. And then it was like the reverse effect when you did a compression.